Cool. Everyone, welcome. Excited to talk today with PsiQuantum about quantum research using Coder. We have a little bit of an icebreaker question. We'll spend some time to let everybody come into the room before we get started with introductions and everything. Um, Note that you'll be able to chat directly through the Zoom or ask Q&A via the integrated chat or integrated Q&A system. We'll save most of the questions for the end. And hopefully, we'll be able to hit a few of them as we go throughout the presentation. But yeah, excited to chat. Hello from Greece. Welcome, welcome. Cool. Evan, I think it's just as people are coming in, we can switch over to the icebreaker question that we have. Awesome. Yeah, gonna highly encourage everybody to use the chat, either during the presentation or just if you have questions or anything you want to discuss. Just to get us started, when you hear about quantum computing, what's the first thing that comes to your head? Is it sci-fi? Is it something maybe related to your personal work? Anything related to research or your academia? Just what's the first thing that comes to your head? And we'll be able to monitor chat as we go. So qubits, the distant future. Maybe not so distant, hopefully. We'll see. $1 trillion, also a good answer. Scientific breakthroughs, of course. Cool, cool. Phase shifts. Maybe the PsiQuantum team will have to help me out with some of the terminology here.
There's some good answers here.
Yeah,
Yeah, I'm impressed.
Knowledgeable.
cool. That's great. We've got the right audience then. Bitcoin encryption breakthrough. Yeah, definitely would be curious to talk a little bit more about encryption beyond 0 and 1. That's great. Cool. We'll give it just a few more minutes and then we'll jump in introductions and some of the fun stuff we got to talk about today. For Evan and Ian, it's probably a little bit different since it's your day-to-day work and you're much more involved in the space. But do you think there's an accurate science fiction depiction of quantum that best represents the field?
Ian, I'll let you take that one. You know more in that field than me.
Science fiction has a lot of bold ideas of what quantum computing is, but really, I think it's exciting and grounded is like the words I would use, which isn't often what you find in quantum compute in science fiction. Normally, you hear words like time travel or I don't know, impossible computing tasks. But no, it's actually pretty tangible, and hopefully, we'll talk through that today.
Yeah, absolutely. I think even just over the chats we've had for the past few weeks, it's become a lot more real to hear about sort of what's coming out of the space. So yeah, I'm excited to get into it. I think we're kind of reaching the critical mass here. We're 5 minutes in. So yeah, I think we can just jump over to introductions on the next slide. First off, my name is Stephen Kirby. I'm going to be hosting today. I'm coming from Coder. I'm a product manager. I've been with the team for about 2 years. I work with a lot of teams on rolling out deployments, just sort of helping with either their AI journey or their CDE journey. And I've been chatting with Evan and Ian a little bit about their work at PsiQuantum, as well as how Coder plays a part in quantum development. So I'll pass it over to Evan to introduce himself.
Sure, yeah. Hi, I'm Evan Glovestad. I've been at PsiQuantum now for a little over a year. I was the first product hire here. And my task as we started out was trying to figure out how do we deliver our tool set and make our tool set more mature and deliver it to the people that need to do research, not just on the hardware side, but mostly on the algorithm side and the software side. That was where my focus was. So ex-AWS before this, was there about 5 years, and an entrepreneur before that again. So yeah, great to be here.
Yeah. And I'm Ian Nanas. I am another product manager here at PsiQuantum, and I manage some of our more quantum-focused tools, specifically around developing quantum applications for the fault-tolerant era, which hopefully will emerge soon. Before this, I got a master's degree at UW-Madison, Wisconsin in quantum computing. And before that, I worked as a product manager at Deloitte for 6 years, and happy to be here today.
Awesome. Awesome. Welcome. Yeah, super excited to have this chat. I think we have a lot to cover today, and I'm super excited to talk about sort of the development of those quantum algorithms that you mentioned, some of the complexity behind there, and how you all facilitated at PsiQuantum. But just to set the stage, could you all share a little bit about just what PsiQuantum does, where your focus is, and sort of what you're trying to solve?
Sure, yeah. So just to kind of kick it off, because I know PsiQuantum is not top of mind of every person in every industry, and that was actually by design as well. We were in stealth mode for about 5 or 6 years, trying to figure out what is the best path to build a quantum computer that is not just proving that quantum is a thing, because that's been proven several times throughout the years, but how do you build one that is actually useful? And scalable, that you can build at, a scale we're talking, millions of qubits, not five, so to speak, because that's the level we got to get to. So anyway, when I started about a year ago, we were about 250 employees. We're now across 500. We came out of stealth about, I think, a year and a half, 2 years ago now. It was shortly before I joined. And yeah, we're the highest, or the best funded pure quantum company, quantum computing company in history. We raised about $2 billion. There's about another couple billion in government grants and initiatives as part of building everything out. And we're headquartered in the Bay Area. We have people pretty much all over the world, in UK, Australia. We have a lot of people. I'm over in New York. And yeah, Ian is over at head office in Palo Alto. And yeah, we've been building this out. We are looking at building the first quantum computers. Actually, just broke ground in Chicago two weeks ago now, on one of the big ones there. So Chicago is one big area for us. Australia is another one where we're building quantum computers. We also made it to like the final round now with DARPA in their quantum benchmarking initiative program. Huge program. It was us and Microsoft that have now progressed to the final stage of performance, which is hundreds of millions of dollars, building out a kind of the larger computers, and they're also going to be part of that Chicago campus together with us and others. So why us? I usually say that, like, what's so special about us? I mean, we think our approach is pretty good. I saw someone did mention LLQC here. It was a good call out. But so optical quantum computers is the approach that we've taken. There's many ways to build a quantum computer or a quantum chip. Our focus, as I said, has been on not how do you build out one that looks cool. You might have seen these chandeliers that people love taking photos in front of. They're very cool, all right? We've been through that as well, and like for testing and everything. But it's like now it's getting real, right? We need to build this up to a certain scale to get to like a million qubits to be able to solve anything useful, right? To get any useful answers out of this. So that's been our focus the whole way. We figured out we have to produce this on chips, on wafers in established fabs. So fabs are basically the ones making chips for everything in your phone, in your computer, everything else. They churn out billions and trillions of these chips every year without hesitation. Um, if you're going to build a huge quantum computer, you should not try to figure out how do you do it yourself, but like how can you fit into their factories and their ordering system so that we like when the process is right. And we had to invent a few things along the way, also in these layers. But then we can produce the chips. We build them into standardized enclosures. We put those enclosures into bigger enclosures, and then into building scale computers. So I saw you came off mute there, Steven. Did you have a question, maybe?
Yeah, I mean, I find this super fascinating. I'm wondering, do you see these once the quantum computer that y'all are making it comes out? I imagine we won't see them like on every desk in every home. But are these things that y'all are going to build as data centers to then serve the qubit operations, or do you plan to see these being deployed in factories? Where are these going to be used?
So, it's kind of one of those like in the eventual time, will we walk around with one of these in our pockets? I mean, I wouldn't rule it out. Like it's, we've been down this path before. We started with building C classical computing as well, and then, now we have it in our phones everywhere. But the initial state here as well is going to be, by 2028 is when we say that we're going to have a building scale quantum computer that can do some useful math, so to speak. And solve some of these algorithms that a HPC computer just can't do today. So it's not a replacement really for classical computers. Like we call it classical computers, right? But think of your normal chips from Intel or AMD or ARM or whatever, classical computing. It's probably going to be a three-way relationship between like classical CPUs, you got the GPUs from the NVIDIAs and others of the world, who by the way is also an investor in our company, and then QPUs, which is quantum computers or quantum processing units. So that's kind of how it's the three-way relationship probably works, is that QPUs are very good at solving a specific set of problems better than anything else, but they won't solve like it just won't replace everything from the go.
Right.
Yeah, it's a specialized tool.
That makes a ton of sense. I'm still excited for maybe the iPhone 37 to have a QPU inside. That's a future I look forward to. As these roll out, what kind of changes do me as someone who is maybe not super familiar with all the algorithms and use cases for quantum computers, how will we see changes? I guess what are the use cases or the applications that y'all are working towards?
Yeah, so it's a good question, and as I said, it doesn't cover everything, right? But there are certain areas that we will see results in earlier rather than later. The ones that we believe that will have useful results coming out of these computers sooner rather than later would be in chemistry, material sciences, pharmaceuticals, as in drug discovery. There's also in energy, things like that. So basically, what you're talking about is anything that has to do with solving nature's equations, right? And testing things out that you just can't do on a classical computer today. Now, what it
Yeah,
actually mean in practice? Well, it could be, things like, yeah, better drugs, for example, as in solving diseases. It could be corrosion resistance, right? It could be solar panels that are way more effective. Things like that. Could be in transportation, solving problems around that. Another, like the holy grail to a lot of things as well, is like, can you come up with a superconductor that can work at room temperature, not at like virtually absolute zero as we do it today? So that's one thing that's going to open up a lot of new possibilities as well. So it's definitely in those areas. Will we get like hoverboards and flying cars? I mean, I would love one personally. So if I can steer them that way for sure. But yeah, that's the kind of innovation that you probably will see first. So yeah, and in drug discovery, it's like, instead of doing some of these experiments that we have to do now to try to figure out like what works and what doesn't, if you could simulate 100 or 1,000 candidates instead and understand exactly what they're going to do, that would be super helpful.
And just add a little bit on why chemistry, and to answer one of the questions in the chat around the size of the computer. The first generations will have hundreds of logical qubits, which means really you have a small amount of data to work with. And you're looking for problems where you have a lot of connectivity between all the different elements within it, a high bond dimension, as chemists will call it. And so that's where you have every single atom interacting with every other single one. And those are the problems that are going to be the first candidates for us to take a look at. Small chemistry problems that will have a large impact in pharma and other industries, as Evan talked about.
That's super cool. Yeah, and I think we can wait on flying cars for these, magical revolutions in the field of medicine and chemistry and energy, which are, obviously some of the most important industries we have. I'm wondering now, since we don't have the qubit, or sorry, the quantum computer today, we're still working towards that. But it sounds like you have a lot of these problems well defined, and you already know sort of what things we're going to be solving with it. How do you I guess, how are you preparing for the delivery of the quantum computer at PsiQuantum?
Yeah, I think that's it's a good segue into the next part as well for Ian. But we definitely because we know what we're building and what specs we're building those to. Yeah, because I mean it's proven out already what we're building. We're just kind of in that scale up and doing some of the improvements in performance. It's really about like if you know that already, we can start doing the algorithms now. But I think on that, maybe I'll hand over to Ian, and then you can go into quantum development and how we think around that.
Yeah. Um, so yeah, there are two parts to the story. Of course, there's building the quantum hardware, which has a lot of work going into it by the majority of the team here at PsiQuantum and building a machine with 1 million physical qubits at a reasonable level of error that makes calculation possible. And then the other half, which is, well, we have this computer, we need tools and we need algorithms to run on it in order to actually drive value and to make it useful. And so that is where our side of things comes from, where we're looking towards how do we develop and refine these quantum algorithms to fit onto early generation hardware. And so that's why we created Construct, which is a suite of different tools that aid the quantum algorithmic researcher in discovering and optimizing those algorithms. Um,
I have a question about that. It's funny to talk about the current day modern or current day compute as classical compute. How do you fit, I guess, these quantum algorithms or sort of validate and test them in the early stages on classical compute? How does that translate? Is there some kind of emulation? What goes on there?
yeah, so we have a few different strategies for going about validating a different quantum algorithm. And the first and most straightforward way is to simulate it. But unfortunately, there's a pretty small limit on the size of algorithm that you can run. Basically, every single quantum bit that you have, in order to fully capture the state that's represented on it, it requires 2 to the number of bits of space. So if you have 2 bits, that's 2 to the 2, that's 4 bits. That's great, that's manageable. But the second you go to roughly 30, then you're at the size of RAM that your laptop has. 31, that's 2 laptops, so on and so forth. By the moment you get to about 50 qubits, it's only 50 bits of data that you're reading out, but the dimensions between them are so high that you have the world's largest supercomputer in the world being unable to simulate this. So you have to look beyond just the simulation as a way of validating these algorithms before they run. And so that's where our quantum resource estimation tools and other different clever ways of validating it take into account. You can look at different subroutines that maybe you don't need the full interconnectivity, the entanglement that you get, and you can simulate these without the quantum rotations. Okay, good. Now you block these off and you're saying these are great, but then there are these other subroutines that have that deep quantum connectivity. How do we go about doing that? And well, you can look at the math, or you can look at how it scales, or you can look at the code really carefully or analyze these diagrams in great detail. And eventually you build up a level of confidence that, yes, my algorithm is going to run when we get the real computer. But there'll still always be that small moment of doubt that we'll have. And when we finally hit run, we might be like, okay, we're as certain as we can be, and we hit run, and we'll be nervous, but we'll be pretty confident that it can work at the end of the day.
Absolutely. Absolutely. It's very difficult to imagine the difference between, an array of classical bytes versus this highly connected mesh of superpositioned qubits. Forgive me if I'm using the wrong terminology there. So can you explain a little bit more on like I guess how these algorithms differ in the word fault tolerance is used a lot, and maybe what tools you provide to specifically engineer these fault tolerant algorithms or the compute to do that, and sort of what gains researchers get by using the tools that PsiQuantum provides.
Yeah. So in the quantum world, just to take a step back, for algorithms research, there are really two different tracks that we have. There's the NISQ era and then the fault tolerant era. And NISQ algorithms are characterized by the machines that they are running on. These are things running on actual hardware like Google's or IBM's machines, which are very well engineered machines and are a cutting edge for what's available to run on the cloud. And these are characterized by having a very, very low error rate, which effectively means you can only do a couple hundred operations before the calculation becomes gibberish, essentially. And so that really does limit the scale and scope of the problem that you can have. Um, Imagine trying to add two numbers together with only 100 different operations on a classical computer. When you actually break it down, you go down to all the NAND gates and AND gates needed in order to make that calculation work. You realize, oh, I've just spent up all of my data, not even adding two numbers, but just loading it in. Uh,
Mhm.
and so when we move to the fault tolerant regime, we see that instead of having hundreds of operations that are possible, we're moving to the realm of billions of operations. And that is characterized by the very, very low error rate that error correction gives our qubits. And that means that we need to start adopting higher level frameworks in order to do this development effectively, because you can't be expected to go through a billion operations with a piece of pen and paper the way you can to optimize it with like a NISQ algorithm. You need different levels of abstraction in your programming languages. You need high level profiling tools in order to count and identify errors easily and automatically for you. Um, you need all of these things. And so the tools that we have at PsiQuantum have been we've worked closely with our algorithms researchers to develop these tools in order to prepare us for this fault tolerant era.
Absolutely. So am I understanding correct that you have a very small sort of context window with the number of I guess concurrent memory positions that you have, but you need to run billions of operations on the smaller state. And can you explain a little bit more what you meant by it becomes gibberish after a while? Is it just that the state simply can't support it? Is there some non-determinism? What do we mean by meaningful answers and like providing stability there with these tools?
Yeah, of course. So with all operations, even in a classical computer, there is a chance that there is an error that happens on your data. So you have, imagine a normal bit where it goes from a one to a zero. That's a bit flip error. And in a classical computer, that exists, and the error of that happening is very, very, very small. And they have a level of error correction in order to make it almost negligible for all computation. Well, those same properties exist within quantum mechanics as well and the quantum computer, but you have two types of errors, bit flips and phase flips of errors. So you have two different types of errors, and your system is less stable because it is quantum. You have photons or atoms in space, and any little disturbance, someone clapping their hands across the room, could, in theory, be enough to cause the data to flip. And if you have 30 qubits, and let's say there's an error for each of them to flip one out of 100 times, by the time you do 100 operations, odds are each one of them is going to flip, but you don't know if it's going to flip or not. And so you can't just flip the data to get out what you want. Instead, you have essentially you can't make sense of what your input is. And so that's why we need error correction in the world of quantum computing as well, which is to make sense of these random flips and to identify, okay, well, that's when it happened, we can correct it, and then we can keep our calculation going. And so that's what the fault-tolerant error is going to promise, real-time error correction so that we can enable longer calculations in order to get to meaningful answers running on actual use cases.
That's super interesting. So not only do you have, a whole other dimension of potential bit flipping, but also phase flipping, but these quantum systems are so much more fault tolerant just because they rely on almost very subtle physical changes in the actual space. It's super interesting. And it makes sense why, yeah, hundreds of operations with a potential massive variance in what could actually be output is way too risky for this kind of work, right? We have two questions. I do want to make sure we have time to go into construct. So I think one of these is kind of technical. I'm going to relay them, and then if y'all want to wait to the end, we can. So what is the best quantum volume formula, and what will be the quantum volume of PsiQuantum's 2028 million plus qubit machine?
Yeah, at PsiQuantum, we use a metric called active volume. You can take a look to read through it, but it's essentially a measure of the number of qubits you have times the length of the qubits. And then you take a look at the empty space in the program and you rearrange the blocks in order to minimize it. There are a couple really strong papers by some of our architecture team you can look through. But if you have time, feel free to read, and if you have questions, reach out. But it could take a couple hours to talk through it in detail.
And it would go way over my head. So I think that's great. And thank you for linking the paper in the chat, Evan. We have one more.
And just to explain like very quickly as well, it has to do with like how many qubits and how many operations, right? But like the way that we do it, highly interconnected, is very different. So,
Mhm.
and that's one of the benefits of photonics. I think another just thing to mention as well with photonics is it's that we can do the active volume, we can do highly interconnected qubits versus some of the other approaches. The other is that we can just run it warmer. Now warmer is on a scale, but and I'll move on to construct here now in a second. But while most approaches that are matter-based do need like so superconducting qubits and things like that need to get down to like 0.02 Kelvin or thereabouts, which is very, very close to absolute zero. We can operate at somewhere between 2 to 6 Kelvin, which doesn't sound like it's a huge difference. It's still, bloody cold, all of it. And you need liquid helium to get it down to those temperatures and all that. But the difference is massive. And that's, again, goes back to the scalability. Because we do photonics, we can scale much higher, much quicker without as much cooling as some of the other approaches.
Super cool.
Yeah.
Cool. For the sake of time, I think we should move on or move forward a little bit and talk about construct a bit more and about how y'all actually enable the real world development of this, and sort of the tools and platform that you built with Coder. I guess, do you want to take it away by introducing us to what construct is?
Sure, yeah. So the challenge we had, and when we reached out to you guys as well, was we were trying to figure out what is the best way of putting our tools in the hands not just of our internal researchers, because they also needed some help in getting access to all these tools and maturing them and everything. It was also trying to figure out how do we bring external partners into our fold and let them use the same tool sets and everything that we had. So what we started working on back last year, about a year ago, was on what we call construct. So construct is, I know platform is a tool that can mean a lot of things to a lot of people, and especially in this context as we're talking now. But the way that we're talking about a platform here is more that it's a container, a delivery container. And I'll talk about also or show, as we go on here, how Coder was a big part of this to power one of these most central tools in this platform. But in the end of it, it's a web-based platform container that contains a bunch of visual tools, online tools, but also needed to give access to some of these more complicated code-based tools for researchers. So when I'm saying researchers, I don't mean hardware researchers or architectural researchers, but algorithm researchers, the ones that try to figure out, once we switch this computer on, someone flips the proverbial switch and says, it's alive. Like, we better have something to run through this thing, because if not, we just built a $500 million paperweight. Like, I don't want to go down in history for that. So we got to make sure we get the right people, the right tools, so that they can line these things up. And then from here as well, we would submit the jobs to run on the actual quantum computers. So this is one of the main tools or tool sets that we wanted to deliver. It's called Workbench, developed in-house by some of the most leading researchers in quantum, and especially fault-tolerant quantum computing, for many years. So we've been working on it for about 6 years. And like Ian was talking about earlier, is that when you start going to FTQC, as we call it, fault-tolerant quantum computing, you need to start thinking more in abstractions and not in specific gates, because like, you'd be surprised but how this has been done a long time. Is like, it's been single gates, maybe drawn out on a whiteboard of like, what is this algorithm going to do. You can do that when you're talking about tens, 20, 100 gates and thereabouts, but when you get into the billions, as we do with classical computing, we don't talk about single bits that we're manipulating anymore. We did back in the start of it, but we moved on from that, right? So we need these abstractions, and that's exactly what Workbench provides. So we came to Coder and we said, hey, we need to find a way to deliver this. We've tried a few different approaches, some more successful than others, but we really want to, we need to step this up, and we need to have it integrated into Construct as well. So not going to go into too much detail on what you see on screen here, just to know that like, some of these things are things that we had to think through and create abstractions for, so that researchers could build these billion operation type gates or algorithms to solve actual useful problems using this quantum computer.
Awesome.
And yeah, one of the tools, as I said, one of the most central tools was our what we call a QDE. Obviously, we'll play on IDE. It's a quantum development environment that delivers. Starting point was, we need to deliver VS Code as a minimum. We want to deliver Jupyter notebooks as well, because a lot of our scientists love working in that. We're trying to find the perfect one. They would deliver this or the other one, and there was no single answer, because some people prefer one, some people prefer the other. So we pretty early on figured out, like, we need a solution that we can deliver both these, but then also future iterations. The whole idea here is to deliver that, hit the ground running. You start it up, whether it's internal developers or external developers, researchers, can start writing quantum code straight away.
That's super cool. And that's something that we focus on a lot with Coder, even for just traditional software developers, is how can we prevent them or keep them spending as much time as they possibly can writing code rather than working on their environment. I imagine that's even more the case when you have all these researchers with deep, deep expertise. I guess you don't want them worrying about installing packages or setting up a Python development environment or setting up CUDA drivers. Just get into the workspace or QDE and start working.
Exactly. Yeah. So, it's complex, libraries and programs that we're installing here. They're rapidly evolving as well. All right, this is cutting edge research. Like, what was cool 2 weeks ago might not be cool anymore, so to speak. Like, things are moving really fast. So we needed to have people on the latest versions, like in these controlled environments. And we were thinking about, like, do we just open source the whole thing and share it out as well, together with there's a lot of other components going to this as well. But we wanted to go this route first to mature everything, to get everything into a good space. There might be a place down the road where we do that as well. But for our enterprise partners, they definitely love this approach of just being able to hit the ground running. And also knowing that their data is safe, because like, I don't want to kind of overstate it, but obviously, people are talking about cryptography and everything. earlier here as well. There's a lot of focus on quantum and not just from like, corporations, everything, but from states as well, because this is obviously something that could potentially revolutionize a lot of applications, both digital and physical. So we're constantly under attack, both, through technical hacks and all that, but also like social engineering and all that. So yeah, we had to come up with a secure solution as well and keeping the IP safe.
And I'm happy Coder was the solution for that. When you were evaluating other tools, was there limitations? Because obviously these researchers are requesting some of the probably the largest machines that have ever been provisioned on Coder.
Yeah.
Did you look at other tools? Did you maybe try building something in-house? What what else? What all went into the? Is there anything else you want to touch on like the decision
Yeah.
process to go with Coder?
Yeah, so there was two iterations before this. Like first iteration was a web-based version of just Workbench, which was developed in-house. It was able to go up to a certain limit, but very, very soon ran out of resources. And it was a little bit of a hard one to maintain as also from a security standpoint. Then went on to code spaces, and it was like, yeah, this works. We tried it with some customers, but like we were not in control of things, and I won't go down into like all the details of what went wrong, but when things went wrong, and multiple things, so we're like, we got to do this ourselves, and we need to do it self-hosted. We can't just like outsource this, and it's just too central to what we do. So we had to build that out right, build it on, and we built it on AWS. So most researchers would have access to like a decent instance to do their, computation and simulations and all that. But because we can do templates and all that as well, we can do templates that give them access to like, metal P3 instances, P4s, all that stuff with lots of GPUs and all that. So, we can do a lot of integrations and things within AWS as well, because we're using this platform to orchestrate it. So yeah,
Super
I
cool.
don't know if that
Yeah.
helps. Yeah.
Yeah, no, that's exactly what I was looking for. And yeah, I would be curious one day to maybe see the actual specs of those machines are being requested because, like we talked about earlier, the scale of these classical machines for even simulation is ridiculous. But I did something that we talked about in a previous call is the difference between I expected that all these quantum algorithms to simulate that sort of parallelism and interconnectedness. You would need a lot of GPUs, but it's my understanding that actually it's GPUs are maybe not the chip you spend the most time in. How does the GPU to CPU ratio work, I guess, when emulating quantum algorithms?
Depends on the scale of the problem and the type of problem, the connectivity. You can get some serious speed ups for large scale problems with the GPU, especially if you use something like a tensor network simulator. But for the lion's share of the work we're doing, we're not testing the largest scale application. And the speed of a CPU is good enough. So yes, GPU is faster, but it's oftentimes not needed because we care more about being able to run a bunch of these quickly with a bunch of small modifications, and that's when the CPU is going to shine.
Super cool.
Yeah, and it's no no secret either anymore, at least, that NVIDIA is an investor in the company, and we're working with them from a partnership standpoint as well, and exploring more of those options as well for simulation. So yeah, I would say that this might evolve over time as well, as everything else we do. Like things change fast here and move fast.
It
Lots of
makes a ton
smart
of sense.
people. Yeah.
Absolutely. It makes sense to have such a strong hardware partnership with a company like NVIDIA when you're getting into at the frontier of hardware development, as well as also have all these applications in the software side needing to leverage that level of compute. I think what would be great to see is a little bit of construct in action. Maybe, I guess, what the flow looks like if we can do a demo.
Yeah, certainly.
Cool.
Great. Do you want to take over sharing there, Ian?
Over.
See if I can do that.
Okay. So now we're looking at construct. I hope everyone can see it fine. But I'll do a lightning tour of quantum algorithm development on our tools. So when you are taking the construct, it's the portal to our tools. I'm just going to be focusing on the QDE, the development environment today, but just to show there's a collection of different tools like the circuit designer, the resource analyzer as well. When you're taken to the QDE, you can start your own instance and access it in the different modalities, VS Code, Jupyter Lab, Terminal if you really want to. And then when you click on it, I'll be in the web instance today. You are taken directly to the QDE. Um, so let me start with a basic example of what some of our tools are, then I'll build it up a little bit. I saw a couple questions in the chat generally around the theme of how are our tools different and complementary to the other quantum development platforms like Qiskit on the marketplace. And hopefully I can see in the code will give a flavor of that. So let me open up my Hello Workbench example to show. Uh, Workbench is primarily geared towards fault-tolerant quantum computing, and that means that there are a couple assumptions we want to make. We want to make it as high-level and user-friendly as possible, and we want to make writing code to be as simple as possible and to minimize the amount of lines and to make it legible. So how do we do that? Well, we take inspiration from classical programming languages that are dealing with problems much larger than the ones we are dealing with in quantum in terms of scale and complexity of program. The first thing is embracing abstractions like different data points. We can see here that we have different types of data points, data types for different integers or fixed values. Here is a quantum unsigned fixed point number, the value, and you can define that in a quantum register, and then you can write the data to it as simply as this. In this example, we're going to be doing some addition. It's a simple task. And so a user would come in, they would type in the number of qubits they want to assign, call it 10. They're going to write in the value that they are adding, and then they're going to print it out. And so we're adding in 3.5. And if you notice here, we have a very simple plus equals syntax. It's the syntactic sugar of doing quantum operations makes programming easier. So when I run my code, you can see here we get a diagram below. This is the circuit diagram, and we're running a state vector sim as well on it. So we're simulating all the bits, and that, as I mentioned before, operates effectively up to around 30 bits of information. Beyond that, it's pretty difficult to simulate given the size, if not impossible. But we can see Workbench. We have a few different features on display here. If that hopefully showcase how writing large-scale algorithms is a bit simpler on with this platform. And so first off, we have the writing coming in. Second, if we look at the circuit diagram, the adder circuit was added, even though the syntax was just the plus equals with a 3.5. I didn't have to assign 3.5 anywhere. I didn't have to write in all the gates. The syntax took care of it for me. And then finally, we have this cool feature where the qubits are being allocated and deallocated automatically. This is a little bit of trickery happening behind the scenes that doesn't exist in other platforms, other packages. It's difficult to do. And so without having to specify that I needed 4 extra qubits to make my calculation work, that's what this specific implementation of an adder does. It's more efficient in some ways and costs more qubits in another way. But in order to do this calculation, I needed 4 extra qubits, and the programming language allocated them and deallocated them automatically, and the calculation was successful. And then we can see some high-level metrics. But
And if I can just say that, like, because you're mentioning like, it's allocating extra qubits and deallocating them, and like in classical computing, that's just normal, right? But in quantum computing, this is not normal. Like you'd have to do this yourself. This is painstakingly using them, moving things, moving out of it, and everything as well, and decomputing or uncomputing things. I just want to highlight like and at a small scale, it doesn't seem like much, but when you get up to the huge scales, all right, yeah.
Mhm.
It's a big
It's similar to how in C programming you have to deal with pointers and you have to put them from here to there and all around. And in Workbench, we try to eliminate all that extra overhead for the user. And then I will hop to a second example just to show, and then hopefully um, this shows some of our tools in use when we get to a larger example. Here, we're going to talk through alias sampling. It's an efficient way of loading data onto a quantum computer. Oddly enough, one of the most expensive parts of any quantum algorithm is efficiently loading the data into the system. And this uses a clever technique using probability distributions to do so. But just to show some of our tools and how they're connected together, we're going to be loading in values from this distribution into it. And then I will show you the circuit that we're doing. So this is our circuit designer tool. It is a collapsible, expandable view, and it's accessible within the QDE itself. And you can kind of see how this routine, this alias sampling routine at a high level works. And it serves as a blueprint for the developer to come in and code it. So when they're going to code through the problem, the alias sampling routine, they would follow this roadmap of having these different parts, the sampling, the swap up, and within the sampling, we have this compare. Within this compare, we have the structure of gates, and all the registers are here. So this is the blueprint that we can use to follow. Now, this whole routine is actually solved within a bunch of primitives that we have. Let me hop down to the section we have here. And here we have our different kubrics. These are our functions that we have. Here's the USP, the select, the QROM, the swap up that we mentioned earlier, instantiated in code. They're pre-made functions that exist in Workbench. If we take a look back up here, the QROM, the prep, the sampling, or what have you, all the different components to it exist. And then we can see within sampling, the compare and the coin toss exist. And it's the same that we have here. And so writing a bit of Workbench code that is complicated, something that is required, can oftentimes be as simple as calling the different subroutines in the proper order and then running them. And then when you run a Workbench, you can see the circuit is generated, and we can verify that the structure is similar to the image that we were trying to go for. We can see the same swap structure and the like. And then finally, we can do some profiling on the algorithm itself. We can figure out how many resources it is, and we can take a look at our resource analyzer. A very important part of quantum development is figuring out, well, what is the most expensive part of my algorithm? And so this is a tool we developed to help profile immediately, and we can see within our alias sampling subroutine at a quick glance, we have the alias sampling. Well, the USP is the most expensive part, with this phase operation being that. And then there's also a flame graph view that you can do to do some quick and efficient sampling as well. Workbench has, and our SDK has a few other features I didn't touch upon, the largest of which is the automatic uncomputation. A big task in quantum computing is you have to calculate a value, do something to it, then uncalculate the same values, because it's actually impossible to clone information in quantum information science. But the automatic uncomputation automatically allows you to take care of that uncomputation by just calling the uncompute method at any level of stack. And so this is what enables us to work at higher levels of abstraction with our toolkit. I know we're short on time, so I will stop my demo here, and hopefully we can open it up to some questions.
Actually, I'll ask the first question about construct. That was a great workbench demo, by the way. Thanks for sharing, and it shows just sort of the simplicity of the UX that you're able to provide given such complex operations, and how much you're able to push away from the user as far as configuring their own or configuring the actual individual sequences that are happening there. I'm wondering, what's the process of actually, once I'm on the construct platform, what's the process of fetching one of those environments? Because in the demo, we obviously saw accessing it through the browser, but I don't imagine this is just running in an application in your browser. What's the process of retrieving and setting up an environment to get into the workbench?
So I think what's different from how most people use Coder as well is that we heavily use the API and have integrated API into our front end. So Ian, I don't know if you could share if you have the construct page open in a browser or something, and just show the QDE page there, so people kind of have a idea what I'm talking about. But yeah, so here's this is kind of how we skinned it, so to speak. And this is our own interface. We can do operations like the operations that we've decided to make available to users. We also use the security, the teams or groups in Coder heavily. We've worked with the team as well on some API functions that we're like, we're really this to work or that work, but team's been great. So we're using the API heavily to orchestrate what's happening behind the scenes. We do allow our users also, if they switch on what's called developer mode, which Ian has on now, then they can access through the button called QD management up in the right-hand corner there. So that one, yeah, they will have access to the actual coder interface. So they can use that as well, but that's not how we mainly interact with these instances.
It makes a ton of sense. And that's sort of our intention too, is just to make sure that it's available however y'all choose to use it. What's the for a lot of people that are considering Coder or using their own development environment solution in-house, there's a long turnaround time on these environments. Since y'all are provisioning such large machines, can you just like real quick, how long does it take for me to get one of these super beefy machines that's set up?
I mean, that's the beauty of AWS, right? And yes, I did disclose I'm ex AWS and all that, but you can get pretty huge machines in not a long time, right? The size of the machine almost doesn't matter for how long it takes. So whether we spin up a full metal instance with lots of GPUs or a small, so we use mostly like dedicated EC2 instances. For call it starter users, we run those on Kubernetes. Both to just conserve resources, and we know that it's not going to be a lot of heavy simulation work as people get started, but then as they go on, we use mostly dedicated instances as well. So they're built within a minute or two. We've looked at the pre-built ones as well. I don't think we need to go that way yet, but it depends. Again, it comes down to the template. So like the standardized template, yeah, that's a minute or two. There's there's certain templates that are for doing some integration work with like CUDA-Q, for example, from NVIDIA. Those do take a lot longer to start up, right? So, or to build that whole environment. So those ones we might end up pre-building. So I think that function is really cool as well.
Super cool. Yeah, thanks for sharing more about that. And we have a lot of questions from the audience. Thank you all for asking so many in the chat. I know, Evan, you've been handling a few async, but I've got a list here. So just using the remaining time, I'd love to jump into these. First, what are the near-term and long-term applications for quantum machine learning once error-corrected quantum hardware and software mature enough for practical use? There's a lot there. So whichever one of y'all wants to take that.
Yeah, quantum machine learning, we don't, I think, focus on as much as we do on the chemistry problems and everything else. But Ian, I don't know if you have anything you want to add around quantum ML.
On quantum ML, we're more focused on the near term, the size of computer you need in order to effectively train models at a scale that outperforms like a large scale data center of the type that OpenAI trains their models on is not in the foreseeable future. And so we're focused more on the quantum chemistry applications.
Super cool.
Yeah.
There was another question from, I think, someone who jumped in a little bit late asking more about the impact. And I was wondering, are there any partnerships that you'd like to mention when talking about those use cases? We talked about how this is going to have huge impacts on energy through solar, through medicine, and through chemistry. Is there any other use cases that you specifically wanted to call out?
I mean, so we are open with some of the partners that we are working with, like Boehringer Ingelheim, for example, on the drug discovery side. We've had some partnerships with Mercedes that have been announced as well, and others like Mercedes would be more in the electric vehicle, battery chemistry, things like that. And obviously, there's through DARPA, there's some government things that we're working on with them as well to verify. A lot of it is around chemistry and simulations of that kind, making sure those algorithms are ready to go. But yeah, if you look at our website, there are some case studies and things like that could be interesting if you wanna dive into it a bit deeper.
Cool. Yeah,
Yeah.
and I guess the website is sort of the direction to get people started in general. Just as a good, I think it's a good call to action there.
Yeah, I
Uh,
saw also, I think it was Iris dropped in there's a YouTube playlist for Construct as well. Go into that one, but then also go into the wider channel. You'll find a lot of stuff. Our LinkedIn as well is pretty active actually. That's all credit to Iris and the team there for keeping that up. But there's a lot of things dropping of things that we're working with, links to everything that's going on. Definitely would recommend checking it out. Yeah.
Awesome.
Yeah.
Sweet. Yeah, I'll be putting that on right after this. Um, so cool. I do. There are a few more here that I wanted to go through. First one's pretty generally applicable. How would you advise technical people to get involved with quantum computing? As speaking as a software engineer without a quantum computing degree, how do you get involved in space?
Good question. So I think you got both people in the room here, right? I didn't come from a huge quantum background. Ian does, and I was more in the AI space over at Amazon. And the thing is, like, first of all, it's the interest, right? Do you have interest for this? Do you want to go into it? Great. Start there. Is this a mission that you want to be part of? If it is, like if it's something you burn for, there's plenty of books out there. Some of them, written by folks on our team. There's one called Programming Quantum Computers from O'Reilly, written by EJ, Eric Johnson on our team. Brilliant guy that's also behind most of the Workbench, or was the main driver for Workbench. So that would be a great place to start. But yeah, that's where I would start. If you don't have like necessarily a quantum background, it doesn't mean that you can't work in this space, because we don't necessarily want, the most brilliant PhDs in quantum computing to sit and figure out how do I write good software, right? So you need that pair between people that are used to making good software and the people that are used to work with quantum research, and get those in the room, so to speak, together. And that's how you build good products, in my opinion.
And then more generally, if you look at PsiQuantum's entire team, you have, in order to build a quantum computer, you have thermal experts, thermal engineers, you have photonics engineers, you have electrical engineers, you have computer engineers, you have all these people, and only a small percentage of them are pure quantum people. You need a lot of different areas of expertise in order to build it. And everyone brings something to the table that is unique and will probably lead to the success of the overall mission.
And I
Absolutely.
promise I'm not getting any commission either from Amazon or Eric, but I just dropped the link to his book there as well, if you want to look at that. We also had, yeah, there's a couple more books as well around this that are written by people on our team.
Super cool.
Yeah,
Awesome.
but it's good pointing, and there's a lot of different areas that we cover with this.
Yeah, I imagine you can't get the whole team in the room just with a whiteboard and maybe Workbench open to work on the algorithms, right? There, of course, is so many moving parts. That's good to know. Cool. And just to keep it moving, because we do have a bunch. This is a question that I'm curious in. As Coder is an open source company, what role does open source play in quantum algorithm development or the quantum development environment? I know we touched on this a little bit. I know it's super important to y'all to secure IP, but where does open source have a role in quantum? Is it too locked down? What's the PsiQuantum take there?
So Ian, I don't know if you want to
Yeah, of
jump in
course.
there.
Open source plays a critical role, I think, in the
Yeah.
development of quantum software. If you look at it internally, we have a couple open source libraries already. Bartik and QRef are the ones I'd point to, and they're for quantum resource analysis and extraction, and understanding how large the circuit is. And the other, QRef, is a common data type that we've developed that can be an interchange between many different systems, and is actually the interchange between many of our own systems internally. Um, so yeah, open source is, I think, critical to developing quantum applications and algorithms in general. And all the different tools out there are exceptional.
That's awesome. And it's great to know that that's also, you mentioned that it's also made available to academia for some of your, for the construct platform itself, as well as,
Mhm.
having those libraries available to other researchers just propels the space, right? So that's great to hear. Um, we are officially at time. I'm not sure if we want to stay over and go through a few more questions. Is there any other specific call to actions? We have the PsiQuantum page. We have the notebooks available that were on the demo today. We also have that YouTube playlist. Is there anything else y'all wanted to mention specifically to the attendees today?
I mean, we're always on the lookout for good people as well. So, do check our recruitment page. But yeah, no, I think those are good places to start. Yeah, as we were saying as well, we need people that know quantum. We know people that need other things. I could not do what I do here without Ian, for example, coming in. Like he's brought in that weird un it's not common experience of like quantum and technical and product management like in one go. So yeah, that's great, to have people like him on a team. Yeah, we're looking for more people, obviously, as we're growing. So
Additionally, like that, if you want to try out our tools, if you want to try a construct, please reach out. We can give access to anyone on the call, and we offer like a 90-day trial of it, and it's free for academics for use as well. So we'd love to have you use our tools and to try them out and to give us feedback. Honest, open feedback will really make the whole thing flow well.
yeah, and I see just one last question I want to touch on. I see Alex there was asking, how do you create new CQDs and do you choose specific compute? Most people are going to be just having one available, like that's where they start. But then we have gated access to some of the other ones where, yeah, they can choose the compute they need for their QD to solve the problems that they need. Some people internally are interested with pretty much free access across AWS, like pick any instance that you really need, while others are more locked down. So again, that's one of the benefits of Coder, right? In using this as the engine.
We're happy to be a part of the story. And I do have to mention the coder call to actions as well. Definitely check out our website and our docs on sort of how we can provide these highly customizable and super accessible environments for really specific or really generalized use cases. We are really focused on the flexibility. So hearing these really crazy ways that people are designing their environments and making environments super accessible to those without a platform engineering experience or anything like that, so they can focus on creating innovation like I'll do at PsiQuantum. It's always great to hear. So yeah. Uh, well, yeah, I think that's a good place to wrap up. Thank you all so much for the chat. This was really great. I'm looking forward to seeing more as PsiQuantum continues to deliver and develop. And yeah, thank you so much.
Thank you, and yeah, feel free to reach out to me or others as well if there's any questions you have as a follow-up. But yeah, thank you for having us today, and thank you for everyone for listening in.
Thank you all.
Thank you.